Welcome to All in All. Today we're taking a deep dive into a subject that's absolutely fundamental to the world around us, especially the digital one you navigate every single day. We are immersing ourselves in discrete mathematics.
That's right. And we've pulled together quite a bit of material for this, articles, bits of research, notes from discussions, all looking at different facets of this really essential area of math.
And our mission really is to unpack all of this for you. We want to go back to where these ideas started, understand why they're so significant, trace their impact, which is pretty wide-ranging, see how this field has evolved, and maybe most importantly, connect it all back to its practical relevance, how it actually works in the world you live in.
Yeah, think of it as getting a really solid handle on what discrete mathematics actually is and why it's, well, so crucial right now.
Okay, so let's unpack this, starting right at the beginning. What exactly is discrete mathematics? That word discrete, what does it mean here?
Well, at its core, discrete mathematics is the study of objects that are distinct, separated. They have countable individual values. The easiest way to get it is often by contrasting it with continuous mathematics.
Like calculus, right?
Exactly, like calculus. Continuous math deals with things that can smoothly take on any value within a range. Think real numbers, like a smooth line on a graph. Between any 2 points, there's always another point. It just flows.
Okay.
Discrete math, on the other hand, deals with things you can count individually, like integers. 1, 2, 3. There's nothing between 1 and 2 if you're just looking at integers.
Or like pixels on a screen.
Perfect example. Pixels are distinct units. Compare that to, say, an old film photograph, which is continuous tone. So we're talking about distinct, countable entities.
Right. Separated pieces.
Precisely. We focus on finite sets, or maybe infinite sets, but ones that are countable, meaning you can basically line them up with the natural numbers 1, 2, 3, and so on. We're counting things, arranging them, looking at their relationships, but always as these separate items.
And this idea, dealing with these distinct, countable things, the sources we looked at really hammer home its connection to computer science.
Oh, absolutely. A phrase that kept popping up is that discrete math is the mathematical language of computer science. And it's not just, related. It provides the absolutely essential sort of virtual foundation for basically every single area of computer science.
Really? Every area?
Pretty much. I mean, think about it. At the most basic level, a computer works with bits, zeros, and ones. Those are the ultimate discrete values, right? Everything built on top of that, how data is stored, how it's processed, how algorithms make decisions. It all relies fundamentally on discrete structures and logic.
Okay, so it really feels like the math that was made for the digital age. But the history, the ideas themselves, they go back way further than the first actual computer, right?
Oh, way further, yeah. When you trace the history of computer science and the math behind it, you're going back centuries. These foundational concepts, they often showed up first in other places, like pure mathematics or even physics, driven by totally different problems.
And the sources point to some really interesting figures who were thinking about these things way ahead of their time.
Definitely. Gottfried Leibniz is a huge one. Most people know him for calculus alongside Newton, but he did crucial work formalizing the binary system, the zeros and ones, foundational for computing.
Right.
His work in mathematical logic was also groundbreaking. And what's really fascinating, as some of the material points out, is his broader vision. He had ideas about computing machines and even touched on concepts that feel like precursors to algorithmic randomness and information theory.
That's that idea about reality being most simple in hypotheses and the most rich in phenomena, and seeing complexity, even in rules, if the rule is super complex, for composé.
Exactly that. It's pretty deep because it suggests complexity isn't just random noise. It can come from intricate but fundamentally discrete underlying rules. It's sort of wrestling with the efficiency of description, which is a core idea in information theory. Is it easier to just list out a complex pattern, or is there a rule, even a really complicated one, that generates it? Leibniz was thinking about structure, logic, complexity, centuries before we really had the formal language for it all.
It's kind of mind-blowing how those philosophical thoughts laid the groundwork. Who else was key in setting this stage?
Well, if you're talking about the logic that actually runs digital circuits, you absolutely have to mention George Boole and Augustus de Morgan, mid-19th century. Their work on Boolean algebra and formal mathematical logic, that's the direct blueprint for how digital systems calculate and make decisions.
The algebra of true-false, Euro 1.
Literally, it's the language of the hardware. And then fast forward to the 20th century, you have Claude Shannon.
The information theory guy.
The father of information theory, yeah. His work on quantifying information, introducing concepts like entropy, it's all deeply rooted in discrete probability and combinatorics. His theories gave us the mathematical framework for transmitting and storing data reliably, fundamental to everything we do with communication and computing now.
Wow. So these abstract ideas, sometimes developed for totally different reasons, they just converge to create this foundation. Even old puzzles played a part.
That's right, like the famous Königsberg Bridge problem. It's often cited as like the first problem in graph theory. The puzzle was, could you walk through the city of Königsberg and cross each of its 7 bridges exactly once?
And you couldn't, right?
Euler proved you couldn't. And the way he did it was key. He abstracted the problem. He represented the land masses as points vertices and the bridges as lines connecting them edges. But modeling the real-world situation with this simple discrete structure, a graph, he showed the impossibility. It demonstrated this powerful idea of using abstraction and analyzing relationships, and it kicked off a whole field of math vital for understanding networks today.
Okay, so these historical threads weave together into the building blocks. Let's dig into the core areas of discrete math that the sources really highlighted.
Right. One of the most fundamental is logic and proof. This is really the study of valid reasoning itself. How do we draw conclusions correctly? What makes an argument sound? It looks at inference, consistency, soundness, completeness in formal systems.
And this isn't just for philosophy class, right? How does this actually apply in computing?
Oh, it's absolutely vital. Beyond just math proofs, logic is crucial for formal verification. That means proving that software or hardware will behave exactly as intended in all situations. Think about safety-critical systems, airplanes, medical devices. You need that level of certainty.
Okay, yeah, that makes sense.
It's also key in automated theorem proving, where we use computers themselves to help verify complex mathematical proofs.
And for everyday programmers, is it still relevant?
Definitely. Propositional logic is fundamental for designing and analyzing algorithms. Those if-then-else's statements, loops, decision points in your code, that's all controlled by logical expressions.
And then there's mathematical induction. It's a proof technique, but it maps directly onto how we reason about iterative or recursive programs. You use induction to prove that your algorithm works correctly for all inputs.
How does that work again?
Basically, you show your property holds for the simplest case, the base case. Then you show that if it holds for some step, it must also hold for the very next step. That's the inductive step. If you improve those two things, logic tells you it holds for all steps. This directly mirrors how a loop processes data step by step, or how a recursive function calls itself.
So it helps you be sure your loop finishes right, or the recursion gives the correct answer.
Exactly. And Boolean logic from George Boole is literally what controls those decision points. The ANDs, ORs, NOTs operating on conditions determine exactly which chunk of code the computer runs next. It's the engine of computation at a low level.
Okay, so logic gives us the rules for reasoning and control. What about set theory? Set theory is all about collections of distinct objects. In discrete math, like we said, we focus on countable sets, finite ones, or infinite ones you can list out. We look at operations on these collections, unions, intersections, differences, and understanding their properties.
And where do we see sets used in computing?
Databases are a huge one. Relational algebra, the theory behind relational databases, think SQL is basically a discrete algebra built entirely on set theory.
How so?
Well, when you do a join in SQL, you're combining data from tables based on shared values. Conceptually, that's like finding the intersection or product of sets and then selecting specific elements, filtering data with where clauses. That's checking for set membership. It's also really important in cybersecurity for defining access control models.
Like who gets to see what?
Exactly. Which set of users has permission to access which set of files or resources? Set theory provides the precise language to model and manage these complex relationships.
And you mentioned something about axiomatic set theory avoiding paradoxes.
Yeah, that was a historical development. Early, sort of naive set theory bumped into some logical contradictions, like Russell's paradox. Axiomatic set theory came later and put it on a much more rigorous footing by defining sets based on a strict list of axioms or rules, which cleverly avoided those paradoxes. It provides the solid foundation that all modern math, including discrete math, rests on.
Okay, logic for rules, sets for collections. What about combinatorics? Sounds like counting.
It is largely about counting, but in very sophisticated ways. It's the study of how you can arrange, combine, and select discrete objects. A big part is enumerative combinatorics, figuring out how many ways you can form certain patterns or structures. Think permutations where order matters and combinations where it doesn't.
And this is useful beyond just, like, figuring out lottery odds.
Oh, much beyond. Though it is used for that. Think cybersecurity again. Passwords and encryption keys. The strength of your password comes directly from the sheer number of possible combinations or permutations of characters.
Right. The more possibilities, the harder it is to guess.
Exactly. A strong password makes the search space for an attacker combinatorially huge. Understanding combinatorics helps you grasp why adding one more character type, like symbols, makes such a massive difference to security. It's exponential growth.
Okay. Makes sense. Where else?
Genetics and molecular biology rely heavily on it. Understanding the possible combinations of genes, alleles, or how proteins can fold. That's crucial for understanding inheritance, diversity, the complexity of biological systems. It's all about combinations at a fundamental level.
Got it. So combinatorics is about the power of structured counting. Now, graph theory, you mentioned the Königsberg bridges. It seems like a huge area on its own.
It is. It's often considered part of combinatorics, but it's so large and important it's really its own field. Graph theory studies graphs, these structures of vertices or nodes connected by edges or links. They are incredibly powerful for modeling relationships between pairs of things.
And they model, well, almost anything involving connections.
Pretty much. Physical networks like roads or power grids, social networks like friendships online, biological networks like how proteins interact in a cell, information networks like web pages linking to each other. The list goes on.
And in computer science specifically.
Oh, they're everywhere. Modeling communication networks, the internet is a giant graph. Data structures, trees, are a specific kind of graph, representing dependencies between tasks in a project or computation, finite state machines that define computational processes. Even the flow of control within a program can be seen as a graph, and they're essential for algorithms doing routing, searching, finding shortest paths, things like that.
What are some of the key ideas within graph theory that have big applications?
Vertex coloring is a classic. The idea is to assign a color, really just a label, to each vertex so that no two vertices connected by an edge share the same color. Finding the minimum number of colors needed is often the goal.
And that's useful for more than maps.
Definitely. Think about scheduling. Say vertices are university classes, and an edge exists between two classes. If they conflict, maybe they need the same room or have overlapping student populations. Coloring the graph is like assigning time slots. The colors. The minimum number of colors tells you the minimum number of time slots needed to schedule everything without conflicts. Resource allocation problems often map to coloring. Spanning trees are another really important concept. For a connected graph, a spanning tree is a sort of minimal skeleton. It includes all the vertices, but uses the fewest possible edges to keep everything connected, forming a tree structure.
And that's good for everybody.
Network design. Finding the cheapest way to lay cable to connect all houses in a neighborhood, for example. You want to connect everyone, all vertices, with the minimum total cable length, minimum weight spanning tree. Algorithms like prims or cryscals find these efficiently.
Okay. And you mentioned network vulnerability.
Right, that brings in cut vertices and cut edges. A cut vertex is a node that, if you remove it, the graph splits into more pieces. A cut edge is similar, an edge whose removal disconnects things. Identifying these is critical for analyzing network resilience.
Finding the weak points.
Exactly. If your graph represents a communication network or power grid, the cut vertices and edges are your single points of failure. Removing them breaks the system. In biology, finding cut vertices in protein interaction networks might point to essential proteins whose malfunction could disrupt major cellular pathways.
It's really powerful how these abstract graph concepts model real-world systems and vulnerabilities. You also mentioned discrete algebraic structures.
Yeah, discrete math makes use of various algebraic structures. We've hit Boolean algebra hard for logic gates in programming, relational algebra for databases, but there are others. Finite groups, rings, and fields are absolutely fundamental in algebraic coding theory.
Coding theory, like error correction.
Precisely. The math behind error-correcting codes used in CDs, satellite transmissions, QR codes, anywhere you need to ensure data is received accurately, even if there's noise or corruption. That relies heavily on these finite algebraic structures. Then you have things like semigroups and monoids showing up in formal language theory and automata theory, which are key for compiler design and parsing text.
And number theory fits in here too.
Definitely. Concepts like modular arithmetic, doing arithmetic with remainders, like clock arithmetic congruences, recurrence relations, these are all core parts of discrete math. And number theory, as we'll get into, is the absolute cornerstone of modern cryptography.
Okay. And just quickly, discrete probability and information theory.
Discrete probability focuses on situations with countable outcomes, rolling dice, flipping coins, dealing cards, analyzing random events in these discrete scenarios. And information theory, Shannon's work, has that core discrete component, quantifying information using entropy, designing data compression algorithms, and again, error-correcting codes, all relying on discrete math and probability.
And discrete analysis. That sounds like calculus, but discrete.
It kind of is. It looks at discrete analogs of calculus concepts. Instead of derivatives, you might study difference equations, which relate terms in a sequence to previous terms. Or you analyze sequences defined only on integers. It's used, for example, to analyze the running time of algorithms defined by recurrence relations.
Wow, okay, so logic, sets, combinatorics, graphs, algebra, probability.
Well,
It's a broad toolkit.
yeah.
But let's step back. Why is all this so essential? What's the real significance and impact?
Well, the most immediate answer, and the sources really emphasize this, is its role as the absolute mathematical foundation for computer science. If you're working almost any CS area, data structures, algorithms, databases, AI, cybersecurity, operating systems, compilers, you're constantly using or bumping up against discrete math concepts.
So you can't really do serious CS without it.
You really can't do it well or deeply without understanding the underlying principles. How do you design an efficient data structure if you don't understand trees or graphs? How do you analyze an algorithm's speed without understanding complexity theory, which relies on logic and combinatorics? How do you manage databases without set theory? It provides the language and the tools.
It feels like it's less about specific formulas and more about learning how to think in a certain structured way.
That's a huge part of it. Studying discrete math develops what people often call mathematical maturity. It's the ability to think abstractly, to formalize problems precisely, to understand and construct rigorous logical arguments proofs. It sharpens your reasoning and problem-solving skills in a way that's directly applicable to tackling complex technical challenges.
So even if you're not writing proofs every day as a programmer.
Right, even then, the process you learned how to define things clearly, how to break down a problem logically, how to consider edge cases, how to reason step by step, that's incredibly valuable for writing good, reliable code. It trains your mind for that kind of precision.
And it opens doors to more advanced stuff.
Absolutely. It's pretty much a prerequisite if you want to go deeper into theoretical computer science, AI research, cryptography, or even many areas of pure mathematics. It's the gateway.
And all this comes together to underpin, well, basically modern technology.
Yeah, its impact is just pervasive, often invisible, but it's there. Every time you use your phone, send a secure email, search the web, run complex software, you're relying on systems built brick by brick using discrete mathematical principles.
From the binary code itself.
And the Boolean logic in the chips, yes. To the graph algorithms routing internet traffic, the number theory securing your bank transactions, the formal languages used by compilers, the logic governing databases, discrete math is quietly making it all work.
Okay, to make this even more concrete, let's dig into some specific examples from the sources. That automated plant watering system is a nice, simple case.
It really is. It shows how even a seemingly simple task boils down to formal logic using Boolean algebra.
So the system has one job. Turn the water on N or OFF, a binary decision.
Exactly. And that decision depends on a few discrete inputs. Is the manual override switch on N? Has the set watering interval passed? Is the soil moist or D or Y? These map perfectly to binary variables, right? 0 or 1. Let's say X is the switch, 1 for ON. Y is the interval timer, 1 if time is up, and Z represents soil moisture. Let's say Z01 for moist, Z is 0 for dry.
And the rule, the logic, is basically water if the soil is dry and the time is up, or if the switch is just turned on manually.
Precisely. And you can write that as a Boolean expression. If dry soil is not Z, so Z, and time is up is Y, and switch on is X, then the condition to water, let's call the output F, is true if Y, A, and Z, or X is true.
So like F, Y, and D, not Z or X.
Exactly. In Boolean notation, you'd write F, Y, Z plus X. This simple formula defines the logic circuit. It takes the sensor inputs, checks the conditions using A and D, not T and OR gates, and outputs a 1ON or 0OF signal.
And the sources gave examples to test this logic.
They did. Let's walk through them quickly. Case 1. Switch OF, XOF, time interval reach, Y1, soil is dry, Z 0. Our function is F1 euro E 0 plus 0. Since 0 not TU is 1, that's F1 euro 1 plus 0 plus 0 1 plus 0 is 1. System turns on. Makes sense.
Right.
Case 2. Switch OF F X0 Interval reached, y1, but this time the soil is moist. Z1 function is F1 euro 1 plus 0, not T1 1 is 0. So F1 euro 0 plus 0 plus 0 plus 0 plus 0, 0. System stays O off F. That's crucial. It prevents overwatering because of the Andy not moist logic.
Okay.
Case 3, switch is on and X1. Let's say the interval hasn't passed Y0 and soil is dry, Z0. Function is F0 up euro plus 1 plus 1 plus 1 plus 1 equals 1. System on end. The OR X part means the manual switch overrides everything else.
That's a really clear illustration. How this basic Boolean logic, part of discrete math, is the engine behind automated decisions, big or small.
Yeah, it shows how these abstract rules directly translate into circuits and actions.
Okay, shifting gears from watering plants to securing, well, everything online. Discrete math is also fundamental for cryptography and security.
It's not just fundamental. It is the bedrock. Modern crypto, especially the public key systems that protect nearly all our secure online activity, things like RSA, Diffie-Hellman, El-Gamal, used for HTTPS, secure transactions, etc., they are built almost entirely on number theory, a branch of discrete mathematics.
And how does number theory provide that security? What's the trick?
The security doesn't come from keeping the method secret, like an old spy cipher. It comes from the massive computational difficulty of certain mathematical problems, specifically problems in number theory. These problems are designed to be easy to compute in one direction, but incredibly hard to reverse unless you have a secret piece of information, the private key.
These hard problems, what are they?
The two most famous examples are integer factorization and the discrete logarithm problem, or DLP.
Okay. Factorization is just finding the prime factors of a number.
Yes, but when the number is, say, the product of two enormous prime numbers, each hundreds of digits long, finding those original primes is incredibly difficult for current computers. There's no known efficient algorithm for classical computers to do it quickly. The time required grows astronomically with the size of the number. This difficulty is what the security of the RSA algorithm relies on. The discrete logarithm problem is a bit different. It's about finding an exponent in modular arithmetic. If I give you numbers g, h, and a prime modulus p, and I tell you that g raised to some secret power x equals h modulo p, finding that specific exponent x is computationally very hard in the right mathematical settings. This is the basis for Diffie-Hellman key exchange and El-Gamal encryption.
So breaking the code basically means solving one of these super hard math problems.
Essentially, yes. The public key lets anyone perform the easy operation, like multiplying the big primes to get the modulus in RSA, or doing an exponentiation in Diffie-Hellman. But only someone with the private key, the original primes or the secret exponent, can efficiently perform the hard inverse operation, factoring the modulus or calculating the discrete logarithm. It's this asymmetry that makes public key cryptography possible. Digital signatures work using similar inverse steps.
Wow. So our online security rests on the fact that multiplying is easy, but factoring is hard for big numbers.
In a nutshell, yes. It highlights how deep theoretical properties of numbers have incredibly practical consequences.
What about computer programming directly? Some students feel discrete math is too abstract for coding day to day. Is that fair?
It's a common feeling, but the sources strongly suggest it's not really accurate. While you might not be formally proving theorems while debugging JavaScript, the underlying concepts, logic, sets, functions, how recursion works, proof techniques like induction are incredibly valuable. They give you the mental framework to break down complex problems, design algorithms that are actually correct and efficient, and reason rigorously about how your code behaves.
Can you give a specific programming example where it helps?
Sure. Beyond the database examples using set theory for joins, think about analyzing algorithm efficiency. You use concepts from discrete analysis, like recurrence relations, to figure out the big O complexity of recursive algorithms. Understanding induction helps you convince yourself, or others, that your loop or recursive function handles all cases correctly. Basic number theory pops up in things like designing good hash functions or understanding random number generators, even seemingly simple things, like how logical operators work on empty collections in languages with features like LINQ or functional programming constructs. Why does checking if all elements satisfy a condition return true for an empty set? That comes directly from formal logic definitions. So it's maybe less about directly applying Formula X and more about equipping you with the foundational thinking tools for building solid software.
Right. The logical precision you learn is the real benefit. And you mentioned game theory briefly.
Yeah, game theory often deals with situations where players make discrete choices that lead to specific, distinct outcomes. While it's a huge field, a lot of it involves analyzing finite games or strategies with discrete steps. It's very applicable to modeling competitive scenarios, negotiations, even resource allocation where you're considering discrete actions and reactions. It fits very naturally into that discrete way of thinking about choices and consequences.
Looking forward then, how is discrete mathematics evolving? Where is it heading?
Well, it's seen absolutely explosive growth, especially over the last, say, 30 years, driven largely by computing and the digital revolution, obviously. It's no longer just for mathematicians and computer scientists, professionals in telecommunications, healthcare, finance, biology, manufacturing, logistics.
Hmm.
They're all using discrete math tools increasingly. It's become essential for anyone dealing with complex systems, data, or decisions involving separate components.
And there's that push to get it into schools earlier.
Yes, definitely. There's a significant discussion about integrating discrete math more into high school and early university curricula. The idea is partly that it offers a fresh start different from the traditional calculus pathway and feels immediately relevant to the computational world students live in. It could engage students who maybe didn't connect with continuous math. Plus, it's seen as a great way to teach mathematical structure, logical reasoning, and proof techniques in a different context.
Is it still an active research area? Are there still big unsolved problems?
Oh, absolutely. It's incredibly vibrant. There are famous collections of open problems in discrete math. Some are really well-known, almost legendary challenges, while others are newer, pushing the boundaries of what we know about graphs, combinations, algorithms, etc. And there have been major recent advances, often using really clever techniques like the probabilistic method or sophisticated algebraic tools.
What's the probabilistic method?
It's a fascinating technique where, to prove that an object with certain properties exists, you show that if you construct an object randomly, the probability that it has the desired properties is greater than zero. It doesn't tell you how to find it, just that it must exist.
Huh. That sounds almost like cheating.
It can feel like it. And that leads to a big challenge in research.
Yeah.
Converting these non-constructive proofs that show something exists, without telling you how to build it into practical, efficient algorithms that can actually find or construct the thing. That's a major focus.
So finding how to build it is the next step. And it's central to new technologies.
Right at the forefront. Take quantum computing. It operates on completely different principles, but designing and analyzing quantum algorithms often requires entirely new, discrete mathematical frameworks. Machine learning and AI are deeply reliant on discrete optimization, graph analysis, and combinatorial methods for everything from model training to interpreting complex data structures, blockchain, and cryptocurrencies. Fundamentally built on discrete math graph theory for the network, cryptography, number theory again, for security, and discrete algorithms for consensus.
And data science, how does it fit in?
There's a huge synergy. With the absolute deluge of data we have now from experiments, simulations, online activity, experts in discrete math are becoming increasingly critical. They bring the theoretical toolkit, the logical rigor, the understanding of graph structures, sets, combinations needed to make sense of massive, complex, often inherently discrete data sets. As one source described it, they connect the theoretical foundations, the hub, to the diverse applications, the rim, in this data-heavy world. They're key to moving data science beyond just finding correlations to actually understanding the underlying structures and causal relationships within data.
Okay, so pulling all this together, discrete mathematics, this study of distinct, countable things, it's really not just some abstract corner of math.
Not at all. It's the fundamental mathematical language. It provides the logical rules, the counting techniques, the ways to model structures like networks, and the operational methods that underpin, well, pretty much all of modern technologies and a huge amount of scientific problem solving.
From the logic gates in that simple plant waterer, to the number theory securing global finance and communications, to the graph algorithms mapping the internet, and the combinatorial problems tackled by AI.
Its principles are just woven into the fabric of the digital world you interact with every single minute. It's what allows us to build, secure, analyze, and ultimately understand the complex, discrete systems that define so much of modern life.
So here's a final thought to leave you with, something to chew on. Given that so much of our world now, the data we create constantly, the algorithms that shape our experiences, is fundamentally discrete, does getting a real handle on the rules and structures of this digital language become, maybe just as essential for navigating the 21st century as understanding the continuous math that described the physical world was for the last few centuries?
That's a really powerful question to consider.
Thanks for listening to All in All.